Alright, so this week we're talking about appliances and the use of standby power. Now, in 2007, Canadians used about 65 petajoules to run home electronics, and that number's actually been going up over time, and 115 petajoules to run the 7 major appliances, which are fridge and stove, which are found in virtually every home, dishwashers and freezers, a little less common, washing machines in basically every home, same with dryers, microwaves also getting there, but a little less common. Now, it turns out that fridges and freezers use the most energy since they run nearly all the time to keep the food frozen and fresh. There's been tremendous improvements in efficiency over the last 20 years now, and the new fridges, especially the Energy Star versions, they use about half the energy of a 20-year-old model. It's a real success story in innovation and efficiency improvements. For instance, this is a photograph I took recently in Future Shop of a new fridge. It says this fridge uses less energy than a 60-watt light bulb, and we'll see in a subsequent calculation that that is accurate. So if you add those two energy uses together, the 65 and the 115, you arrive at 180 petajoules for appliances across the country. Dividing by the 12.99 million households, that gives about 13.8 gigajoules per household of energy for appliances. This compares with the 66 gigajoules for home heating, the 18.8 gigajoules for heating water, and then the 4.3 gigajoules for lighting that we've already seen. So it's a significant amount of energy. You know, it's basically 3 times the amount of lighting and comparable, but a little bit less than the energy for heating water. So this is about 14 32-watt light bulbs that are on all the time. Now, we're going to be using over the next week or two a device known as a watts-up meter. And what it will actually do is if you plug something in, it'll measure the power that the appliance is drawing as a function of time. Now this is interesting because appliances don't make a steady draw. Right? If we look at an experiment here that I did with my own home fridge, we'll see there's an initial spike that goes up to about 900 watts. Okay? But it doesn't stay 900 watts. It's only 900 watts for just an instant. So the power rating of the fridge is that maximum reading. But it doesn't actually hold that for more than an instant. So my fridge, you could see, is about a 900 watt fridge. Okay? But of course, most of the time, it's a lot less than 900 watts. So this is the instant or maximum power. What's the average power? Well, the watts-up meter will measure that for us because it'll measure the power here, that initial spike coming from the compressor. And then this is while the compressor is running and circulating the refrigerant fluid. And after a while, when the temperature reaches the desired level in the food compartment, the compressor gets shut off. There's a little thermostat. Now it stays shut off for a while until thermal energy from the room leaks in and the temperature increases to a certain point where the thermostat triggers again, and then boom, the compressor goes off, you get a big draw, the compressor runs for a little while, the temperature drops back down, etc., etc. So we look at this full cycle here from when the compressor initially fires until it's just about to fire again. And the watts-up meter can tell us how much total energy was used. It's actually just this area here. So I measured it, and I found that the fridge used 113 kilojoules over a 2358 second cycle. So what's the average power there? Well, let's scroll down a little bit here and work that out. A power is still an energy over a time. So we are using 113 kilojoules. That's 113,000 joules over, oh goodness, okay, this is energy over time. And where did that other zero go? 113,000 joules over 2358 seconds. So let's see what that is on average, the average energy use by the fridge. It's going to be a lot less than the maximum rating of 900 watts. So let's just work it out on the calculator here. So it's 113,000 divided by 2358 seconds. You see it's actually only 47.9 watts. So on the previous page when we said less than a 60-watt light bulb, that's accurate. So the fridge uses the same amount as a 47.9 watt light bulb on all the time. Okay. Now that, of course, is going to change because if you open the fridge door and the thermal energy from the room rushes in, then the compressor will have to fire more often, and you'll end up using, that cycle will take less time, and therefore you'll be drawing more average power. If it's really a hot day outside, then by Fourier's law, because of the higher temperature difference, there'll be a greater thermal energy flow into the fridge, and again the compressor will fire more often. So this number will vary from day to day over the course of the year and with usage patterns. The 900 watt peak power is going to be the same each and every time, right? That's the initial firing of the compressor. So this is a really interesting device, this Watts-up meter, because it enables us to look at our appliances and see how much energy they're drawing, not as a maximum, but as an average over time. So we've got about 47, 48 watts here for our fridge. Let's look at a different appliance, a microwave. Now, we'll introduce a concept here, standby power consumption. What is that? Well, that's the consumption of power when the device is just sitting there not doing anything. So let's underline that or highlight it. So, with fridges, you have to leave them plugged in all the time, okay? Because otherwise your food will go bad. But microwaves spend a lot of time just sitting there doing nothing. And when they're doing nothing, they're still drawing power because of the clock is on. It's a similar thing with computers. They still draw a little bit of power to keep the battery charged and to undergo basic system maintenance. Cell phone chargers still draw a little bit of power through the transformer coils. This is really just wasted energy. Let's see how much from the microwave. So here's a graph of a microwave. This is my microwave at home again. It's a 2 kilowatt or 2,000 watt microwave, and so there's the peak power when it's actually on. Okay, it draws that much, but of course you probably only fire it for a few seconds, and then it just sits there. And when it's sitting there, though, it's still drawing 3 watts of power. That's 3 joules per second, which doesn't sound like a lot, but it's a lot of seconds. When the door is open, the light goes on, and so there's a little bit of a, you can't see it, but there's a little step there. So there the light's on, okay? So the microwave went on, it stopped, I opened the door, the light went on, then I closed the door again, and the power went back down to 3 watts. So let's see, over the course of a week, I estimated, I use my microwave, not a whole lot, about 45 seconds a day. Let's find how much power we're drawing on standby, and then, or how much energy we're using on standby compared with the actual energy we use when we're cooking. So, cooking energy, let's do that first. That's going to be smaller. Now, since power is an energy over time, and energy is a power multiplied by a time. And the power, oh, that says cook, so that's supposed to be a C. Cook. Doesn't look like it, but it's a C. Cook energy, E for energy. Power, when you're actually cooking, we can see there is, what was that, 1950 watts? Yes, 1950 watts. So that's 1,950 joules each second. But we're only on for 45 seconds a day. Okay? So let's just do this daily use here. Over to the calculator. So we've got 1950 joules each second for 45 seconds each day. That work out? I think that's right. 1950 times 45. There we go. So it's 87 kilojoules a day of actual cooking energy. Okay, let's come back here. Let's tidy this up a little bit. Make that look like an equal sign. And come on, make it look like an equal sign. There we go. And let's see if I can fit this in here neatly. 87,750 joules. Okay, so that's the amount that's used for actually cooking. Now let's see how much is consumed on standby. Okay, the standby energy, again, will be the product of a power and a time. That says equals. Let's write the formula again. Power times time. So the power on standby is only 3 watts. That's 3 joules every second. But how much time do we have? Well, a day, 24 hours, is 24 hours times 3,600 seconds. There's 86,000 seconds in a day. We said we use the microwave for 45 seconds. That means the other 86,335 seconds, the microwave is just sitting there drawing power for the clock, by the clock. And so if we multiply that 86,000 seconds by the 3 watts, we find that there's actually 259 kilojoules, as opposed to the 87 kilojoules that we actually used cooking. We're actually drawing 259,065 joules just sitting there doing nothing. Okay? So that's basically 3 times the energy that we actually used in cooking just going to waste. So it's a good idea when you're done cooking just to turn it off, because this energy really, although it ultimately ends up heating your room, is not, you're not making especially good use of your energy. So that's our class for today on power used by appliances and the concept of standby power.